Hi everyone, welcome back to our Calculus 3 class notes here on page 94, and we're in section 15.4 right now, where we're learning about double integrals but with evaluating them using polar coordinates. So I want to do an example. Find the limits of integration for integrating f of r theta over the region r that lies inside the cardioid r equals 1 plus cosine theta and outside the circle r equals 1. So first of all, the circle r equals 1, that would be x squared plus y squared equals 1, right? Or the square root of x squared plus y squared equals 1. Either way, square root of x squared plus y squared is r, so r equals 1. So that's this circle. The cardioid is, let's see, if I start at theta equals 0 and I sweep it out just to kind of see what the shape is. When theta equals 0, cosine of 0 is 1, so r is 2, starting right here. If I sweep across to pi over 2, cosine of pi over 2 is 0, so r equals 1. Sweep down to pi. Cosine of pi is negative 1, so 1 minus 1 is 0. That's why it loops back into 0, and then it just repeats the same as I go around. Okay, so we want outside the circle but inside the cardioid, so that's this region I've shaded in. So the limits of integration, so for dr, so first of all, remember that your dA becomes r dr d theta. So I'm going to look at the inside limits first, find the r limits. So the lower function, or the function that's lower and it's trying to enclose this in, is the function 1. So r goes from 1 up to the function r equals 1 plus cosine theta. So that would be your limits for r. Okay, and as r is doing this, theta is sweeping from minus pi over 2 over to pi over 2. Or I could say, since this is a symmetric area here, I could go from 0 to pi over 2 and just double it. Okay, so that would be how I would set up my limits of integration. Then I would need to know the function of r and theta here. Now, just like we could before when doing area in rectangular coordinates, I just would have the area, which is the double integral over r of dA, and then dA is dy dx, and I have to be able to describe r, or dx dy for dA, either way. So dA now for polar coordinates becomes r dr d theta, and then I describe r in terms of polar coordinates. So we've already done it for this problem. I just want to continue it here. So I actually just want to find the area of that region that we drew on the previous page. So in other words, I'm integrating the function 1, right, just like I have here in function 1 dA. So I'm just integrating this r dr d theta. So I set it up so we have dr on the inside. So the integral of r is 1/2 r squared, evaluated from r equals 1 to r equals 1 plus cosine theta. So I get 1 plus cosine of theta squared minus 1. So this is 1 plus 2 cosine theta plus cosine squared theta minus 1. So the 1's cancel, and I get 2 cosine theta plus cosine squared theta. Now, a very, very popular trig identity that we will use to evaluate things like cosine squared is that, or sine squared as well, it just becomes 1 minus here, but cosine squared theta is 1 plus cosine of 2 theta over 2. So this is actually on your formula sheet that you're able to use for the exams, but just quickly, we should understand that cosine of 2 theta is cosine of theta plus theta. So cosine of alpha plus beta is cosine alpha cosine beta minus sine alpha sine beta. So if I have cosine of theta plus theta, that's cosine squared theta minus sine squared theta. And then 1 minus sine squared theta is another cosine squared theta. So that's 2 cosine squared theta over 2. And that's why this identity is correct. But now I can integrate this. So I get 2 sine theta for integrating cosine theta. Then I have a half I have to integrate, so I get 1/2 theta. And then cosine of 2 theta over 2 becomes sine of 2 theta over 4, because integral of cosine is sine, but I have a constant there, so I divide by that constant. So that gives me sine of 2 theta over 4. If you don't quite understand that, why you're dividing by that constant, you just do a u substitution, u equals 2 theta, and you can see how that works out. Evaluate that from 0 to pi over 2. Plug in pi over 2, I get 2 times the sine of pi over 2 is 1, so 2 times 1 is 2, plus 1/2 times pi over 2, so that's pi over 4. Sine of 2 times pi over 2 is sine of pi, which is 0, and then minus, plug in 0 for theta everywhere, and I get 0. So write 2 plus pi over 4 as a single fraction. The common denominator is 4, so I get 8 plus pi divided by 4.